Okay. Welcome everybody, and thanks for joining to today's lecture on sustainability in computer science. Specifically, today's topic will be about green HPC, paving the way to or for sustainable supercomputing, which is a bit of a catchy title. But still, I would like to tell you a little bit about what's going on in supercomputing and HPC with regard to sustainability, focusing specifically on energy and power concerns. So first of all, what is green HPC? When we talk about green HPC, first of all, there's the high performance computing component. High performance computing, according to Wikipedia, means that it uses supercomputers and computer clusters to solve advanced computation problems. Personally, to me, I always consider it HPC when we need to spend some significant amount of effort in not only getting to the result, but thinking about how we get to the result. So whenever we need to deliver results really quickly, whenever we are somehow resource constrained, whenever it starts to matter how we do things and not just what we do, then I consider it HPC, even maybe, for example, computing on my laptop or a desktop PC or something. And then, of course, there's the green aspect where we consider green HPC to be environmentally friendly. I have two examples here on the slide. On the very left, some of you might remember that's a photograph taken in 2010 when the Deepwater Horizon oil spill happened, a huge environmental disaster. And these days, we already have the knowledge how to do simulations to predict what will happen, try to confine any oil spills, maybe possibly even prevent them. But we still need a lot of computational power then to actually solve these problems. And right next to it, there is an image of a plant growing on some PCB, because I found this in an HPC Wire article. I thought the image was extremely silly, so I immediately added it to my presentation. And on the right, you just see some visualizations of simulations, which we frequently do in HPC. The first one being air turbulence generated by the landing gear of a Boeing 777 airplane. And on the very right, Earth's magnetic field deflecting solar winds, so charged particles that are hitting us all the time. And we try to simulate and model how much protection we might need or might not need, and so on and so on. So pretty diverse and pretty interesting results. Now, I will mainly focus on energy consumption here, or power consumption. And the question is, why this is relevant in HPC? Why am I focusing almost the entire lecture today on energy? And before we get to that, a small disclaimer: when I talk about energy consumption, I'm well aware that energy cannot be consumed. It's always being transformed from one form to the other. But for the sake of simplicity, let's just call it energy consumption for today. But of course, all the time we're talking about actually transforming electrical power into heat energy, for example, or heat power. So an example that I want to give is Frontier. It's the fastest supercomputer currently worldwide, located in Oak Ridge in Tennessee in the US. On the right, you see a photograph of some of these racks with all the compute nodes inside. And Frontier is really extreme by any standards in terms of computing and storage. So it has almost 9 million cores, even though one has to admit that they are counting CPU cores and GPU cores, but still 8.7 million is a huge number. They have almost 10 petabytes of main memory available, coupled to those cores. They have more than 750 petabytes of storage available. And what's pretty important and significant for the system are not really these numbers, but the measured peak performance of the system, which is just over 1 exaflop, which has been sort of a magical number that we were trying to beat and break through for the last couple of years. For those of you who don't know the term exaflop, this refers to 10 to the power of 18 arithmetic floating point operations per second. So every second, this system can do 10 to the power of 18 floating point operations 1 second after the other, which is a huge computational power. And of course, we don't get that computational power for free. We need to spend some energy and electricity on it. And so the system has pretty high electrical and thermal operating requirements. First of all, I could just give you the number. I could say that it consumes 23 megawatts of power during operation. But one important thing to note here is, regardless of these numbers, for all the modern HPC systems and for all the supercomputers, the main limiting design factor these days when you design and build these systems is really the electrical and thermal requirements these systems have. So it doesn't matter how much money we can get together. It doesn't matter that we need to build buildings for those supercomputers. We need to find space to build those buildings. It's really only about supplying enough electricity in some feasible and economical way and being able to get rid of the heat that is generated. That's really the main limiting factor in how large we can build these things. But coming back to this number of 23 megawatts, that might not be very telling. So how much is 23 megawatts actually? What can we get out of that? This can be actually visualized in a nice little chart where we say, okay, it would be the power consumption of one frontier supercomputer. I just told you about it. Also, it would be less than half of what the next number one or expected number one supercomputer will be, which is called Aurora. And it will probably be unveiled in a week or two at the supercomputing conference when they will publish the numbers, and it's expected to hit the next number one, consuming 60 megawatts approximately, which is a lot. Compared to the city of Innsbruck, the Frontier supercomputer consumes 1/3. So it means you can get 3 of these Frontier supercomputers and you would consume the same amount of energy or power that Innsbruck takes on average, the city of Innsbruck, which is pretty impressive considering the IKB, the Innsbrucker Kommunalbetriebe, which are the main utility provider, have 11 or 12 hydroelectric power plants working around the time. And 3 of those supercomputers would easily fill this budget. So that's quite amazing. And also it's more than 7 times the power consumption, the average power consumption of the University of Innsbruck. And the University of Vienna takes twice the amount of power apparently to operate. Those are numbers that I found published on the university websites. So it's still more than 3.5 the power consumption of the entire University of Vienna, which is pretty impressive. Also, of course, in a sort of negative way, and that's why we are working on this topic and why we are interested in green HPC. The problem is we want to optimize the energy consumption. We want to minimize it, obviously, or minimize the power consumption, but we cannot optimize something without measuring it first. So what we need is we need some kind of power or energy instrumentation in order to get some data. And after we have some data, we can try to build some models and we can try to optimize for that. Now, power and energy instrumentation has been a sort of dubious topic for the past couple of years. On the right, I'm showing some photographs of experimental research devices like these industrial grade power meters, for example, that you can buy for a couple of €1,000, or some homemade tools that can also measure power or energy consumption. But the problem with those is they might give you accurate results, but they're really only suitable for experimental research. You can't buy 1,000 of these things in order to measure 1,000 nodes in a supercomputer. It simply doesn't scale that far. Also, these devices sometimes can be a fire hazard. I remember talking to a colleague at a conference in Hamburg, I think in 2014, where they did something like you see in the lower picture, directly attaching leads and getting measurements of a compute node. And they ended up actually burning up the motherboard on their first try, and they had to order another one from the vendor. So these things are not to be toyed with. Modern supercomputers gladly have these things built in by now because it's becoming such an important topic that the devices you see on the right are really only required for experimental research if you want to do some special thing. But for general measurements, most modern supercomputers have this available off the shelf, so to speak. And on top of that, there's a plethora of power and energy models that are built on these measurements, like linear models or even AI-based models. Some are better, some are worse, but speaking of experience, I would always prefer actual measurements because you simply know what happened. You know that you're doing actual physical measurements, because a lot of models simply give wrong impressions if they run with the wrong workload. In any case, after you have data available, we need some metrics, of course, to be able to tell what's going on. And 2 prominent ones are the power usage effectiveness, the PUE, and the energy delay product, the EDP. They are both available in the green HPC field, but they are coming from very different perspectives. So the PUE is important to data center or HPC operators because it compares the total facility energy, so the amount of electricity essentially that you pump into the entire facility, the entire institution, compared to the amount of energy required just to run the IT equipment. And ideally speaking, you arrive at a PUE of 1, which means all the energy you put into the system or into the facility is actually used for the HPC computing system. And the other one, the EDP, is an important metric, and there are various derivatives of it. From a software perspective, when you're trying to optimize software running on a given system, which simply multiplies the energy consumed by the wall time in order to somehow have a singular metric for both how fast the program runs and how much energy it consumes, and trying to minimize that minimizes both energy and wall time at the same time. There's a lot of controversy about both of them, but anyway, 45 minutes lecture is not enough to give you a detailed overview of all of this. Those are probably the two most important and two most prominent ones if you want to get into the topic. Now, what can we do with such metrics? First of all, we can establish nice rankings. So first of all, there's the top 500 list. For those of you who don't know, it's a list of the fastest supercomputers worldwide, released twice a year. And basically what they do is they're just competing or battling rather for the fastest system to get the number 1. It's always a competition between various countries and various institutions. At the moment, you see an excerpt here on the right, which shows the 4 fastest systems. At the moment, Frontier, as I've said, is number 1. Number 2 is the former number 1, Fugaku in Japan. And number 3 and number 4 are actually pretty nice because they are European systems coming out of Finland and Italy, both via the Euro HPC initiative, which means all of us can get comparatively easy access to those systems, which is pretty nice. What they essentially do with these systems is they just run some benchmark, in this case, mainly the high-performance LinPack benchmark, which is just some linear algebra stress testing, so a lot of matrix multiplication and LU decomposition and all of these things. And of course, you could use this list to establish which is the fastest system, how much faster is it than the second system, and so on and so on. But personally, I find it more interesting to build various analyses and statistics around trends, for example. So comparing over the years, how did supercomputing evolve? Which architectures are in place? What's the market share of specific technologies, and so on and so on. As I've said before, this list is released twice a year. At the moment, the June 2023 edition is current, but in November, in a couple of weeks, we will have a new one with likely Aurora in number 1 here. And what's important also is that power consumption is now an integral part of this list. So on the very right, you see a column that reports the power, in this case for Frontier, about 23 megawatts. And you won't find this data for all the top 500 systems, especially for the slower ones. They're usually not affording to do this. But for the top ones, it's basically reputation if you add the power consumption. But also there's the green 500 list, which does the same as the top 500, but they're not only going for speed, they're going for energy efficiency. And this is actually pretty intense because there's a specific document of 33 pages with definitions on the measurement devices that are allowed to be used, the topology of these systems, workload requirements, what statistical means are allowed to be used in order to do averaging, whether it should be the arithmetic mean, the geometric mean, and so on and so on. And what you arrive then is at a ranking, as you see on the right here, where we have energy efficiency rankings with the top system here at 65 gigaflops per watt. And you also see the top 500 rank here included, which is definitely not directly correlating to the green 500 rank. So the most energy efficient system is by far not the fastest system worldwide. So there's always some kind of trade-off. Regarding the document, I don't want to go into details because that would take far too long, but the only thing I want to mention is there are multiple levels of measurements that can be taken from level 1 to level 3, and they basically increase the strictness of the measurements and how much of the system has to be measured, so the scope of the measurements. Level 1 only requires to measure some part of the application, some part of the cluster, and you're allowed to extrapolate and so on and so on. And moving down to level 3 means you need to measure your entire application. You need to measure the entire supercomputer, all the components, and so on and so on. And this is pretty detailed. So there are just some examples here on the, or some executive summaries here on the slide, which are not that significant. But if you're interested in the topic, you can go ahead and read the document. I can send it to any interested people, and it's pretty intense and pretty detailed. Now, as I've said before, it's interesting to analyze these lists because of trends. And one of the first things we can do is analyze the power consumption of the past systems when we project them to be 1 exaflop systems. So we didn't have this before Frontier, but how much power would these systems have consumed if they had been built to the size of 1 exaflop? And as we can see, if we compare the top system in the green 500, which is the red line, and the top system in the top 500, which is the turquoise line, you can see that this is ever increasing. And consider that the y-axis here is a logarithmic plot. So you can see that as we progress throughout the years, the performance, the power consumption that is required in order to reach the performance of 1 exaflop is ever decreasing, which is a good thing. At some point, we will hit this magical boundary of 20 megawatts, which is what people a couple of years ago thought was the limit of how much electricity can be feasibly supplied to a supercomputer. But knowing that Aurora will easily beat this and Frontier is already 10 or 15% above this, this limit is no longer. But still, that's still sort of a benchmark line for people when they talk about energy efficiency or power efficiency. Now, if we want to optimize, there are several avenues of optimization. And in the next couple of slides, I will talk about various things that can be improved. For example, we can increase parallelism. This is something that already happened in the past. I'm just going to go through a very brief historic overview. We can work a lot with cooling. I'm going to spend a lot of time talking about this because this is where the main gain comes from. And of course, we can also decide what hardware should be used and how this hardware should be used. How the hardware should be used is especially relevant to us software developers if we want to optimize for energy efficiency on a fixed platform that we cannot change, but we can change the software that you write using different tool chains, using different software techniques, and so on and so on. But what's important to note here is whenever you work with energy efficiency, it's always a multi-objective problem. So it really rarely happens that you're only optimizing for energy consumption or you're only optimizing for power, because usually optimizing for one of those two means you're always sacrificing a little bit at least of performance. Sometimes you're sacrificing a lot of performance. And this always leads to a multi-objective problem, which I've visualized here on the right. Those of you who have worked with this before might know the Pareto optimality problem, where we have a couple of solutions to our problem, optimizing for one objective, for example, time, and a second objective, for example, energy. And at some point, you will likely arrive with multiple points where one of these points, one of these solutions does not dominate another point because one is better in one objective and the other one is better in the other objective. And you have to choose between one of those two, or you have to choose among them. And you will always have to sacrifice one of the objectives. And this is something that we have to deal with every day when working with energy optimization. Now, regarding the brief historic overview, so what can we do here? This is microprocessor trend data that I like to show a lot also in my own lectures because it gives a pretty nice illustration of what happened about 20 years ago. What you see here are columns of markers, and every column, like this one or the one next to it, represents a specific processor microarchitecture or processor generation. And for each processor, we see the number of logical cores, the typical power consumption, the frequency, and so on and so on. You could analyze this figure for a lot of things, but the important things are the 3 metrics that I selected here, because we see, for example, the black markers, the number of cores has always been consistently 1 until around 2005 or so, and then we started to see multi-core and later on many-core CPUs. So why was that the case? At the same time, while this happened, you see that the frequency increase that has been happening throughout the 80s and 90s suddenly flattened off and stopped. So starting around 2005, 2010, we are no longer seeing a significant increase in the clock frequency of the CPUs, but it's flattened off, and at the same time, the number of cores increased. Why? Because the increase in frequency was no longer feasible. Increasing the clock frequency of a CPU up until a certain threshold consumes so much power and energy that it's no longer feasible to provide electricity and also to cool the entire thing. This is also evident by the red markers here, which is the typical power consumption, which is flattening off roughly around the same time. It's a little bit more varied or a little bit more diverse, but you can still get the general picture. And this is the main reason why we don't have CPUs these days that are clocked at 10 or 15 gigahertz, because we cannot provide the power to make the thing operate reliably, and we cannot dissipate the heat quickly enough. And people thought, okay, let's not increase the frequency, let's add multiple cores and move into parallel programming. That's a little bit bad for us software developers, because the frequency increase back in the 90s was essentially for free. If your software ran too slowly, the only thing you had to do was simply buy a faster CPU. Buy a CPU of 2 gigahertz instead of 1 gigahertz, and your software might run twice as fast. Depends on the workload, of course, but still. These days with parallel programming, it's no longer that easy. We need to implement and design our algorithms in such a way they can actually make use of this increase in parallelism, of these additional cores, which means now we software developers, or those of you who are software developers, actually have to make use of these additional cores manually. It's not just something that you get for free, which unfortunately is bad, but at least we still get an increase in performance. That's the good thing. Something else that can be observed is an ever-increasing number of accelerators. So what you see on the right here is, again, trend data of the top 500 list from November 2010 to November 21. And this is the number of systems in the top 500 that have accelerators of some sort, whether they are GPUs or something else. And you see that basically this is ever increasing. There are some phases where it's decreasing, the largest one around here, 2015, and those are pretty easily explained. For example, this one is when Intel canceled their Xeon Phi brand, which was apparently an economic failure. But beyond that, beyond such small impacts, you always have an increase, and sometimes quite a steep increase, in the number of accelerated systems. And why is this the case? Because accelerators and accelerated clusters provide some of the best cost and energy efficiency in HPC. If you have programs that are suitable for GPUs, for example, it's almost impossible to beat them in terms of cost efficiency and in terms of energy efficiency. This is also evident if we look at the top entries of the Green 500 list. For the November 22 list, all 10 out of the top 10 entries are accelerated clusters. There's no cluster without accelerators in the top 10 of the Green 500. And 9 out of those 10 systems use GPUs, and just 1 system is using another accelerator type. Another perspective is looking at those top 10 systems dependent on their power efficiency, specifically if we draw a line at, say, 10 gigaflops per watt. If we check which systems are above this 10 gigaflops line, for the top 10 systems that I mentioned before, 8 of them above this line use accelerators, and there are only 2 exceptions that manage to get beyond that even, which are Fugaku. Fugaku is a Japanese system that is using ARM-based processors, so it's essentially the same technology we have in our smartphones. And some other system that is pretty efficient is the Tianhe 2A system, which uses Matrix 2000 accelerators. And those are also RISC CPU cores, which are not as efficient as GPUs, but still efficient enough to be quite high in the top 500 list. And for the other systems, we see the Summit and the Sierra system and so on. Most of them are using normal GPUs, in this case NVIDIA, because NVIDIA has been quite pervasive in the past. But AMD is coming back now with their Instinct GPUs, and so far they seem to be doing a pretty good job at it. So Intel is also getting back into the business. It's going to be quite interesting because there's more competition, and more competition is always better for us customers or users. And another perspective we can take at that is the power efficiency depending on the architecture, like the specific GPU model or accelerator model. For this chart here on the x-axis, you see various accelerator technologies, including none, which means those are systems not accompanied by any accelerator. And these dots that you can see throughout the chart, it might not look like it, but in total, there are really 500 dots in this graph, just overlapping a lot. And on the y-axis, you see the performance, the power efficiency that we can get, so performance per watt. And we see among the lowest energy or power efficiency are the systems without any accelerators whatsoever. There are some outliers here that try to be quite efficient, but most of them are really coupled down here. And the systems that achieve a very high efficiency are systems equipped with the NVIDIA A100, for example. And there's also a cluster down here, which is more efficient than the non-group, but still not as efficient as those. And they are powered by NVIDIA Tesla V100 cards. And that makes total sense. If you don't know, the V100 cards are simply an older generation than the A100 cards. So this is simply the more modern technology. Those are more power efficient or energy efficient, but still any accelerator on average beats systems without any accelerators. And the two far outliers here on top, which manage to beat all the other systems, are specialized systems that use specialized cores for AI workloads, for example, that are not vastly used by other supercomputers. So those are really corner cases, so to speak. Now, what can we do? I told you that we can increase parallelism. We can try to work with accelerators, but is there also something we can do in software in order to optimize? And this is where tuning comes in. There's a lot of research in software for coming up with a means to reduce energy consumption while still arriving at the same computational result. I'm showing here two examples of my own research, quite some years old, but still valid nonetheless. On the top, you see a figure that illustrates the overhead in energy and time when you compile programs with the GCC compiler compared to an IBM compiler and then running the binaries on an IBM CPU, specifically the IBM Power 7. So this was to figure out how much more efficient is the IBM compiler on the IBM CPU compared to GCC when we look at how efficient are the binaries that are produced out of these compilers. And in general, you could say, okay, we have here positive numbers, which means that's the overhead of GCC over IBM. So GCC is usually producing slower binaries or producing binaries that are less energy efficient because for this case, for example, they consume 45% more energy compared to the IBM compiled binary. But what I found very interesting is that there are cases where this is actually not the case. There are cases where the binary produced out of the GCC compiler is actually more energy efficient. And I found that quite funny, considering that IBM is both designing and building the CPU and also designing and building the compiler, but they don't manage to be better across the board. And sometimes going below 30% performance degradation or energy degradation is quite a lot. So I found that pretty interesting. Naturally, this doesn't really boil down to the compilers, but actually the instruction mix. But from us, from a user perspective, the choice of compiler or the choice of compiler flags is really what we can influence. So that was the point of this research. And another example is the bottom figure, where we are investigating different DVFS settings of an experimental Intel chip, the Intel SCC. DVFS, for those of you who don't know, is a dynamic frequency and voltage scaling, which means the CPU can clock down and be slower while saving a lot of energy and power if it doesn't have a lot of work, especially during idle times. So this is something that all our systems do every day. Our smartphones, our smartwatches, laptops, and even server and supercomputing CPUs do this nowadays. And the important thing here is that the energy optimal setting is neither the highest nor the lowest clock frequency for most systems, but something in between. So for this benchmark on the Intel SCC, the optimum was 320 megahertz, for example. And where this sweet spot is, where the optimum is in terms of energy consumption, really depends on your hardware platform and also depends on your workload. If you switch the workload, if you switch to a different program, this optimal setting changes or might change. And this is where we have to do analyses and figure out program behavior. And this is something that's used, for example, in supercomputers. So the SuperMUC at the Leibniz Rechenzentrum in Garching, next to Munich, they are using an energy-aware runtime system where you run your program once and it's analyzed. And if you run it again, they take database data, historic data, that tells them how efficient your program can make use of these higher clock frequencies and automatically select an optimal setting to be most energy efficient. You can override this if you want the energy, if you want the result really fast and you don't care about the energy consumption. But if you don't manually override it, they will automatically reselect a new frequency the next time your program runs, depending on the program's characteristics, which is pretty nice. I told you we're going to be spending quite some time talking about cooling. And when we talk about cooling, I always have to mention VSC3. Because there is a ton of funny stories that can be told about this system. So the VSC3 is or was the fastest supercomputer in Austria back in 2014. Worldwide, it ranked number 85, which is pretty decent considering the limited budget we have available in Austria for these things. Consisted of 32,000 cores, consumed about 0.5 megawatt of power. And remember, we talked about the power usage effectiveness, and this system had a PUE of 1.02. So they call it a mechanical PUE, which means it's only the HPC system and it's cooling, but not any of the surrounding infrastructure. So it's a partial PUE. But still 1.02 is a pretty nice value. And back then in 2014 and 15, we basically hit the news for that because many systems didn't manage to achieve that. The previous system, the VSC2, for example, had a PUE of 1.18, which is significantly higher. And the VSC4 system that followed later on, which was water-cooled, is 1.05. So why do I mention water-cooled here, and why do I say oil here? So you see a photograph on the VSC3 here on the right. And normally, you know, these supercomputers, if you've seen any pictures, of usually these really high racks with compute nodes stuffed into them, lots of cables, blinking lights, and so on. And this somehow looks different. They more look like boxes. And there's a very specific reason for that, because these are actually oil tanks, essentially. So what they did for the VSC3 was they basically built these tanks, filled them with oil that was electrically non-conductive, and basically submerged the compute nodes vertically into these oil tanks. This technology is called immersion cooling. If you really put the entire technology that should be cooled into the liquid, into the coolant. Since the oil was not electrically conductive, there was no shortcuts, nothing happened except for normal operation. And because oil has much better thermal conductivity properties compared to water, this is much more efficient. So there was no need for any fans like air or a lot of pumps. The only thing you had to do was pump the oil through those tanks, but the nodes themselves, they were completely passively cooled because you just submerge them in the oil, and convection, heat convection in the oil will do all the work for you, basically. As you might have seen, the VSC4 was water cooled again, and I'm pretty sure people will never do this again, at least not that quickly, not on that scale. One of the reasons, for example, is I'm not sure if you noticed, there are some paper towels here lying on the floor, and this is not by accident, because oil essentially creeps everywhere, and people were actually slipping and hurting themselves while doing maintenance on this machine. So there are also some spots down here. I'm not sure if this is visible through the screen share, but using oil is very efficient and at the same time a huge pain to work with. So for larger scale systems, this is probably not going to happen again. But still, back then, we basically hit some records in terms of efficiency of what was possible back then. So it's pretty nice. Now, if we can't use oil because it's too complicated, what can we do instead? And what people mostly do these days is use direct water cooling. And remember, I told you it's always a trade-off between something, energy, and something. In this case, it's maintenance effort. So water is much easier to deal with. What you see here is an illustration of SuperMUC nodes, again, the supercomputing system in Munich, which has a lot of copper piping with water flowing through, in this case, through the GPUs, and also here on the left, the CPUs, and also in the back, the PCI Express controller, and also the storage subsystem is water-cooled. And these nodes just have connectors and pipes going in with cool water going in, hot water going back out. And basically, they built a couple of thousand of nodes like that and cool them like that with direct water cooling, where the water is essentially in direct contact with the CPUs or the chips to be cooled. And on the right, you see a photograph that illustrates how tight the tolerances are on that. Because, for example, what you see here is the processor cold plate, as they call it, which is essentially just a cooling unit. Below this thing, you have the actual CPU. And I'm not sure if this is visible on the screen share, but here you can see the order in which these 4 screws should be removed, and also the order in which the screws should be installed back. And below that, there's even the torque, how tight these screws should be fastened. All of that is precisely specified to make sure there are no leakages and to be sure that there's full contact, so you're doing the most efficient cooling possible without the CPU having to clock down because of thermal issues, for example. And here I have a small GIF illustration that just shows how the water is pumping through the system. So we have cool water coming in here, going through the individual chips and going through the PCI Express controller. And while it's heating up, it's turning into red because now it's hot and moving back out. And we have a couple of thousand nodes. And if you want to repair one of those, for example, you just have to disconnect here to make sure there's no leakage, pull the entire thing out, and then you can work on it, which works pretty well so far. So this is basically state of the art what people do. Coming to speak of state of the art, there are very few other choices. You could do air cooling, but air cooling, while it's easy to build and maintain, is quite inefficient because air is not a good conductor. There's direct water cooling, differences between warm and cold cooling. Warm just means that you're not actively cooling down the water. So the inflow, the intake temperature can easily be 50 or 60 degrees. Cool water or cold water cooling means you're actively cooling down the water using like a refrigerator or a heat pump principle. But this again takes electricity. So we're trying not to do this. But this really depends on where you have the computing site, because for warmer climates, sometimes you don't have the option to only deal with warm cooling because it's not cool enough on the outside. So this can be an issue. And sometimes there's even indirect cooling, which basically just means that you're cooling with air and then you're cooling the air with water. And this is what people did until like 10 or 15 years ago. And it still pops up somehow. On the right here, you see a survey of European systems back in 2020. And indirect cooling is still an option, but very few systems are using it these days. Then how is this energy used? Because we can, of course, reduce the energy consumption. We can reduce the heat, but some heat will always be there. And this is where reuse comes into play. So I have here a graph of some data center in the US, which shows what happens with this energy. So we put electrical energy onto our flag HPC systems, for example, flagship systems. This is cooled, and the hot water then is immediately used for cooling the office buildings, the campus, using floor heating or something similar, for example. So trying to reuse the heat and not just dissipating it out into the outside world. Once we reused all the heat we can, we have to dissipate it, of course, but first we try to do it passively before doing it actively with actual cooling towers that require power. And then basically we finish the entire loop going back into the system, first cooling some legacy systems that are still using air as an intermediate coolant before moving back to the flagship system that can deal with direct cooling. And on the right, you see a flow of electricity where, again, the large scale or the biggest part is going into the flagship system, only a little bit into the legacy IT systems, and very little into air conditioning, for example, pumps, the actual cooling, all the lights of the buildings and so on. All of this really needs to be taken into account when you decide how energy efficient a system really is. Yeah, and this is just another graph that shows it from some IBM research project where they try to build systems with hot water cooling, which means a large or high inflow temperature rather of 60 degrees, outflow of 65. So there's very little temperature difference here. And the 65 degrees is easily enough, for example, to heat office buildings, to heat homes, and so on and so on. And this is actively used in a lot of sites these days. So this is really what people do these days. Now, we always talk about sustainability with HPC and sustainability for HPC or computer science in general. I want to show that we're not only working on HPC itself, of course. There's the figures on the right side, which try to make energy, try to make HPC more energy efficient by deciding which tools to use, for example, or how to operate the hardware. But of course, we can also use HPC to optimize stuff that is not HPC. On the top here, there's an illustration of a wind turbine, essentially, trying to simulate all the turbines and optimizing the shape of the blades, for example. And on the lower image, it's more of an indirect sustainability issue because, for example, those are crash test simulations of cars. And once we can figure out better how these crashes come to be, how material strengths can be simulated and computed, we can maybe spend less material on the car, make the cars lighter. And if we have lighter cars, we need to spend less energy on moving them. So there's a lot in HPC going on that gears towards sustainability, but it's more indirect because it's not directly related to power or energy. And there's only one example here because there's really a lot of them out there. Of course, it's not all fun and games. There are some pretty significant open issues. First of all, there's more than just energy and power. If we move into usage, there's of course also carbon usage, there's water usage and space usage. All of them have their individual usage effectiveness metrics, and usually data centers or HPC centers always select the metrics they like the best because they appear the best in those metrics. So it's always some kind of marketing scheme, I guess. Also, I did some research for this talk today and tried to find more of this usage effectiveness for data centers and HPC centers to compare them across various metrics. And it's really difficult to find a complete set of numbers because they don't like to publish numbers that don't look good. Besides that, even if we stick to power and energy, there are too many metrics, seriously, and many of them are inaccurate. So there's the power usage effectiveness, we talked about that. Then there's a partial PUE if you don't measure the entire machine. And also apart from that, there's the energy reuse effectiveness, and there's the energy reuse factor, which takes into account how much of the heat that's generated is actually reused before it's dissipated, which is not really taken into account by the PUE. So that's difficult. And also these metrics are partially flawed because, for example, the PUE cannot be used to properly compare HPC sites in different climate zones because that would be unfair. You really can only use the PUE to compare sites in same or equivalent climate situations with same ambient temperatures or average temperatures. That's something that people often overlook. And always, of course, you have diverging interests. So there's the operator that tries to minimize the power and energy consumption because they have to pay the bills, they have to pay the electricity bills, and these things cost a lot of power. I think the VSC3 electricity bill back then was close to €500,000 a year to operate it, if I remember correctly. Larger systems are easily a couple of million euros per year just for paying the electricity bill. Then there's the user who wants to minimize the wall time because they want the results to be available as fast as possible, obviously. And there are taxpayers and politicians who are often looking to minimize costs. Not necessarily all the time, but of course, that's also a valid consideration that needs to be taken. And of course, this is a multi-objective problem that we're dealing with here. Now, what are some future developments and ideas? So where is technology taking us? First of all, there's high bandwidth memory, which basically means we're trying to increase the bandwidth and decrease the latency of memory that previously has been physically separate from the CPU or the computational units. And now we try to put them together as close as physically possible because we really want to minimize literally the travel distance of data, because moving data is really expensive in terms of the energy required and also time because of the speed of light. So it's really about the physical distances on chip or on the main board, which we try to minimize. Then there's the fabrication size reduction, which a lot of you might know because this is about the nanometers that are reduced ideally contiguously or continuously every 2 or 3 years, although we're running into more and more problems about that. And current research thinks that we are unable to go below 2 nanometers, whatever that means exactly, because it's not a universally defined metric across vendors, unfortunately. But anyway, after some certain limit, we have to move away from silicon because silicon chips cannot be built below some threshold and still deliver correct results, unfortunately. So there's a lot of research going on there. And there's also something called near threshold voltage computing, which means we operate CPUs below safe power limits where the CPUs actually make computational mistakes. But we take into account that they make these mistakes and we try to run iterative solvers or approximative algorithms that are anyway approximating towards a result. So maybe we just need to do a couple of more iterations, but while doing so, we can save power because we can operate the CPU at a much lower power limit. And you can easily save a factor of 5 or a factor of 10 of power consumption, running them below safety limits and taking into account that they will make computational errors and 1 + 1 will not necessarily be 2. And use iterative solvers to mitigate that and work around that. Then, of course, there's special purpose hardware like accelerators, FPGAs, and so on. And most easiest would be to, in terms of energy efficiency, would be to have custom hardware designs, but these are pretty expensive. This essentially means building a custom chip for your very domain-specific problem. And you can do that. It costs a lot of money, but then you are about as energy efficient as we can be these days, I guess. And something else that's quite interesting is optical computing. People are currently researching whether we could use photons instead of electrons, for example, because that would be much more energy efficient. But to be honest, it's not clear yet whether this is actually a viable alternative. There's a lot of research going on in this area, but people are not sure yet because there are some roadblocks and we don't know if we can get around them yet. So I have no idea, to be honest. I find it very interesting, but this is something that will happen if it happens in 30 years from now, probably. Maybe never. Let's see. But anyway, it's a pretty interesting approach. Something that I would like to close with is more a physical or a philosophical discussion, maybe, which is the issue of reversible computing and the Landauer principle. So I'm no physicist, but sometimes I read books about physics, and apparently there's a theoretical lower limit on energy consumption if we talk about thermodynamics, which is called the Landauer limit. if we do a irreversible computation, which is what we do all the time, on the right, I illustrate an AND operation, which means 1 plus 0, or 1 added with 0 equals 1. And doing this operation, we lose information, because after this has finished, we don't know if both inputs have been 0 or if one of those inputs have been 1. We can't distinguish these cases anymore because we lost information. Apparently, if we lose information, this must be accompanied by a corresponding increase in entropy and therefore increase in heat in a closed system, because thermodynamics, apparently. This is pretty interesting because the Landau limit has some specific number. Apparently, it's 0.0175 electron volts, or 10 to the power of minus 21 joules. So a really small number. And we are really several orders of magnitude away from that. We're really far away from that. However, there's something called Kuhme's law, which is similar to Moore's law. If you remember, Moore's law is about performance roughly doubling every 2 years. And Kuhme's law says that the number of computations per joule, so the energy efficiency, doubles every 1.6 years. If we couple that with the Landauer limit, that means we cannot increase efficiency, energy efficiency, any further in 2080, which means after 2080, if all our technologies hold and if we do everything that can be done, after 2080, we won't be able to increase the energy efficiency because we've hit the physical barrier of what's possible. And this apparently also applies to quantum computing because it's about physics. I found this pretty interesting, although I don't understand all of it, but apparently that's what researchers who are experts in this field say. And apparently the philosophical solution to this would be reversible computing, because we got into this problem in the first place because we're doing irreversible computing, because we're losing information. So if we were to switch to algorithms that would do computing that could be reversible, where we are not losing any information, we wouldn't necessarily have to have any increase in heat and therefore no increase in entropy. Whether this holds, whether this makes any sense, I don't know, but I would say it's a pretty interesting approach, and probably even further away than optical computing. So with that, I'd like to close today's lecture. The biggest takeaway, or the most important takeaways here, are that there's a lot of research and engineering going on, both sustainability for high-performance computing and also sustainability with high-performance computing. And the by far most important thing is that power and heat are the main limiting factors in how large we can build these things. That's why almost everybody uses water cooling these days. Waste heat is recycled as much as possible and ideally freely cooled afterwards, not actively chilled. And the short-term developments are quite clear, and how much benefit we get out of them. The long-term future, at least to myself, is very unclear, and I'm very curious where things will go. If you're interested in talking to me about these topics further, there's my email address and some other contact information. And with that, I'm open to questions.
Thanks, Philipp. So get a couple apologizes. We are not able to hear her regarding technical problems, and their audience, feel free to write questions into the chat.
Why not build all HPC clusters in the Arctic is a question given by Joachim. Well, that's a very good idea. Unfortunately, I would guess, I'm not sure I'm entirely qualified to answer this question, because I think a pretty big portion of that is politics for no reason whatsoever. But also, of course, electricity, because you need to build these things where you can provide the power. Remember, I talked about this 20 megawatt power limit that was sort of this important number in everybody's head up until a couple of years ago. So the biggest design criteria was not really how much energy we can put into the system, but rather where is the next power transformer or electricity station, where can we build our supercomputer so it's really close to where the energy is generated. Similar to Germany, for example, where they try to build power plants that are burning coal next to the coal mining sites in order to minimize the moving distance of the coal. So I guess that's a big part of it. There's a lot of data centers, as you write yourself, in northern Sweden, for example. People are really trying to make use of this as much as possible, but there are various reasons, both technical and societal, I guess, and politics especially, which simply make this unrealistic. It would be nice to change that, but sometimes it doesn't work. And to a very limited degree, I guess it's data movement, because if you're moving a lot of data, the fastest thing is actually to physically ship hard disks. And this can be quite painful if you build systems in the Arctic, I guess. I hope that sort of answers your question. Do we have any other questions?
So I try it again. Can you hear me, Philipp?
Yes.
Yeah, here is Gerti. Okay, excuse me that I'm, you know, do not show my screen. I'm sitting in a car and it is dark anyway. So, and we have learned in the second last presentation, we should turn off our videos to reduce the energy consumption. Thank you very much. It was, I always say this is like reading a crime story. It was really the same also for your presentation. Very interesting. I would just have one question concerning, you know, this your philosophical last slide. But even at the very end, if we have all this information, reversible computing, isn't it also that we then would need more energy to come to a solution?
Possibly. To be honest, I'm not qualified to answer this question because I don't entirely understand this myself.
Yeah.
I'm not embarrassed to say that because I'm not a physicist, especially not on that level. But yes, to the layman, it would seem that initially this doesn't make sense because you would probably need to do more operations, and more operations would require more energy consumption. But maybe this induces some kind of mathematics that we don't have available yet, or some kind of technology like quantum computing, for example, which works completely differently compared to what we are used to in classical computing. So I'm not sure. I find it extremely interesting, but I didn't dig down far enough to understand this, and I'm not sure I can without a physics degree, to be honest. I'm a computer scientist, so.
Thank you.
We do have another question. How realistic is it to use renewable energy as power sources for HPC? That's an interesting question. I would say to some degree it's realistic, and it's probably already being done actively, because there are lots of data centers that are being powered, for example, through solar energy, because Google and all these big data center providers are using these photovoltaic systems on top of their buildings because they have the money to afford this. And also on the long run, it really makes sense in terms of energy expenses. But also it's not that easy. So I can try to switch to a backup slide here. This is the power consumption, so the power draw of the SuperMOOC system in Munich over 5 days, I think in 2017, yes. And what we see here, we see a lot of different numbers. I don't want to spend too much detail on this figure, but the important thing here is the black line, which is the total power draw of the entire data center, and these dashed red lines, which are the predefined power bands that the SuperMOOC data center should stay in. And should stay in because they consume so much power. They, of course, have dedicated or separate contracts with the utility provider, with the electricity provider. So as long as they stay within this power band, they pay a fixed amount of price per kilowatt hour. If they go above the power band, if they consume more power or energy compared to what was in the contract, they, of course, have to pay extra. The funny thing is they also have to pay more if they go below this, because that's unexpected. And if you draw less power, less electricity from the grid, the utility providers need to react this and change the power production, so to speak. The power grid is something, the electricity grid is something that always needs to stay in balance. And so if they go below this limit, they also need to pay extra because that's not what was agreed initially. So ideally speaking, it should be a constant line. And unfortunately, with renewable energy consumption, with wind energy, with solar energy, at the moment, it's pretty difficult to establish a fairly constant flow of electricity. So to some degree, data centers are already powered with renewable energy these days. fully, at least with the current technology, I guess it's not possible yet, but maybe we're just missing the right combination of wind turbines and hydroelectric power plants and e-fuels, for example, to take off the edge of the spikes. So who knows? Timo has a question. Are there any noteworthy clusters with a focus on efficiency, or any languages compilers that have a focus on efficiency, especially for HPC? Clusters, yes. I mean, for the clusters on focus on efficiency, you really only need to look at the green 500 list. So I already showed this before. The top 4 systems are given here. If you Google for green 500, the first hit will definitely take you there. And all of these systems are compared with regard to their efficiency. So how many arithmetic operations can they do per energy or per power spent? Regarding languages and compilers, this is more difficult. First of all, because yes, there are vast differences. There are some statistics or tables floating around that compare programming languages like C, C++, Java, Perl, Python, and so on. And they show how extremely efficient C or C++ can be and how inefficient Perl can be or something. And I really don't like this comparison, because if you work with different programming models, if you work with different programming languages, it takes you a lot of time not to learn the language, but to truly master it and to be able to program and implement things, not just by any means, but in the idiomatic way that was intended by this language. I can write efficient programs in C, and I can write very inefficient programs in C. And the same I can do in Python, in MATLAB, in Julia, or whatever you're using, or other parallel programming models like OpenMP, MPI, and so on and so on. So it's really difficult to do a fair comparison here, because you would have to have people that are really competent and capable in all of these programming models. And that means knowledge and experience of 5 to 10 years easily for each programming language, and then implement an algorithm and then compare the energy efficiency. So there are some languages that are more efficient. There are some languages that are less efficient. Some random example, for example, is Go. The Go language has a certain boundary checks in its makeup that are difficult to get around. So there's a certain lower limit that you cannot get around, and it's easier to get around this with C or C++ because they don't have these boundary checks. But since I'm not an expert in Go, and I'm probably not going to call myself an expert in C++, even though I do a little bit of programming, it's very difficult to make any statements here. But in general, people try to be more efficient, of course. It's a more important, ever-increasing important goal, but it's really difficult to do a proper comparison here. I hope that's answer enough, at least for a short run. Marco, what about components of supercomputers? Is it more difficult to replace it, and how much higher are the risks of data losses than by a typical computer? That's a broad question. So what you need to be aware of when you build a supercomputer, these things are usually large, and they consist of several thousands of components, which means something will always fail. If you have your computer at home, something, for example, the memory modules might fail. If you build 5 computers yourself and you own them over 20 years or something, which would be pretty long, I guess, at least one memory module might have been broken. Maybe you already experienced this in your past. If you have a couple of thousand memory modules in your supercomputer, 2 or 3 or 4 of them will break every day. And every day you have to swap them out. So usually people simply adhere to the principle of a maximum wall time, where it says, if you're running a job on a large supercomputer, you're only allowed for a maximum of a couple of hours. On most systems, it's 24 hours. On the very long-running systems, it's a maximum of 72 hours. After this, your program has to stop anyway and restart. So you do a kind of checkpoint restart approach. This is mandatory on all the larger systems. And this sort of gets you around the problem. If your program crashes and it ran for a day, you simply reschedule it and it will take another day. But ideally speaking, they are not budgeting you for this loss because it was not your fault and there's no big issue. It's not like you're using weeks and weeks of computation. On the other hand, there's a lot of research going into resilience and how to build these systems such that if a node breaks down, another node can take over on the fly. It doesn't make sense to build nodes or try to build nodes so they don't fail. It's hardware, and hardware will always fail at some point because it's physics, it's materials, they break at some point. But we try to do a lot of research in software means how to mitigate that and how to work with failing nodes. but I have yet to see a large-scale system where this is actually in production and working. We did ourselves a research project, a Euro HPC project, or a Horizon 2020 actually, on this, and unfortunately we couldn't find any production system to try this because they're simply not equipped in order to do that. I hope that answers your question. But you could spend hours and hours talking about this. So at least consider all the cables. I once visited the Marconi system in Bologna of Cineca, which is the Italian National Supercomputing Center. And they are swapping on average 1 optical fiber connection per day because it simply breaks, because the lines are running through various rooms and the rooms have different temperatures. So there's a temperature gradient inside the optical cable. And apparently that breaks the optical properties of the cable, of the fiber, after a couple of years. And then they need to swap the cable. So this happens on a daily. So every day, at least 1 or 2 of these cables are replaced with new ones because they break. So that's just what you have to accept when you work with large scale systems. You are welcome. Do we have any further questions? Do you think the RISC-V poses some potential for more energy efficient processors, accelerators in data centers, or are future improvements more or less agnostic to the concrete instruction set architecture? A question by Johannes Bies, which is a very specific question. That's difficult to answer because it always depends on the workload that you have available. So first of all, RISC chips can be extremely efficient. We've already seen this happening with ARM chips. If you remember, let's just go 1 slide back. The current #2 system, which was previously the #1 Fugaku, is made of Fujitsu A65FX chips, and those are essentially ARM chips with 48. Here it says 48 cores. For most of these chips, it stands to reason that they are equally capable of running normal workloads compared to normal x86 chips, which is a CISC architecture, so complex instruction set architecture, and of course much more complicated, much more power and energy hungry. But it's possible that these kind of RISC chips will replace x86 on the long run. However, all of them, at least the way it currently looks, will always be coupled with accelerators of some sort, because still RISC chips are too general purpose to beat something like a GPU or a properly configured FPGA with respect to the specific workloads or programs that they are suitable for. Just like you wouldn't try to run a computer game, the render software of a computer game in software on your CPU. You have a GPU for that, and it's designed to pump out pixels, compute pixel shaders, and so on as fast as possible. The same probably holds for supercomputing. So I would say that yes, probably RISC chips will have more potential in the future, but I don't think they will ever replace accelerators, because dedicated hardware is simply too optimized and too fast in order to be beaten. The question is just how much dedicated hardware we want to have, because GPUs and accelerators in general, they now are suitable for scientific computing. They are suitable for AI because people added these data types and so on and so on. There are a lot of workloads, a lot of programs for which GPUs are a bad choice and you shouldn't use them, for which general purpose CPUs will always be better. So designing domain-specific chips for every domain science out there, like chemistry, biology, and so on, is probably not feasible because it costs a ton of money to build chips and design chips in the first place. But it stands to reason that RISC chips in general will probably be a main competitor to the x86 chips that we see at the moment. In the past, we even had Intel 64 architectures, which is different compared to x86, and also IBM Power CPUs, which are still around these days. And those two types are not x86 chips. But yeah, let's see. In any case, there will always be improvements that, as you said, are agnostic to those instruction set architectures, like specific ways of optimizing software, clock frequency operations, and so on. Those are completely orthogonal to these issues.
Great, thanks, Philipp. Thanks for your presentation, it was very interesting. And also thanks for the audience, because we are already 6 minutes over. Philip, if you can send the slides to Gerti, would be great. And
Will do.
Thanks to the audience for this session, and I will see you next week for the next session. Have a nice evening.
You too. Thank you. Bye.
Thanks. Bye.